Our next presentation is about Boehmite needles in Corundum, and that they are actually rose channels. It'll be presented by Dr. Emmanuel Fritsch from the University of Nantes. Thank you, Emmanuel.
Thank you very much, Shane, for the introduction. Yes, so there is an old trend of the gemologist. This is when you look at natural corundum, you often find what is called Boehmite needles. You're taught that they are Boehmite needles, so you repeat they are Boehmite needles. But for the last 30 years, perhaps even more, there have been gemologists wondering if they really are Boehmite needles. And Frank Notary, which from the GGTR labs in Switzerland, and his colleagues Candice Kaplan and Thomas Heinzfang, have been wondering about that for a long time, and we're looking at stones. And over the last probably 15 years, we've been trying to understand if they were really Boehmite needles or not. Now, what are Boehmite needles? They are crystallographically oriented, one-dimensional, tube-like inclusions in corundum that you see very well. And as you can see on it, rather spectacular purple sapphire from Tanzania, which is worth more for its Boehmite needles than for the rest of the stone, perhaps. So they are very easy to recognize inclusions. And as you got the general idea in the previous picture, these needles are near perpendicular, but if you measure actually with great accuracy, you realize they are not quite perpendicular. They make an angle of 86.1 and 93.9 degrees. And that does represent actually the edges of rhombohedron. You see them here, so the dotted blue lines represent the direction of the so-called Boehmite needles. Okay. Another characteristic that you can see on even not very nice stones like this one, which is literally filled with this kind of inclusion, is that this inclusion occurs at the intersection of twin lamellae. They are not twin planes, they actually have a certain thickness to them. So it remains, the corundum remains essentially a single stone. You can appreciate it's a twin here because you see in polarized light some differences in color and atmospheric effect or interference effect that you can identify. Now, if these are Boehmite needles, logically, we should see the characteristics of Boehmite accompanying them. And you should see in particular the best way to identify Boehmite is the infrared spectrum. There are two bands here around 1990 centimeter minus 1 and 2120 centimeter minus 1 that are quite characteristic of Boehmite. Boehmite is one of the polymorphs of the aluminum oxyhydroxide. Diaspore is the other one, which has similar actually spectra, but they can still be distinguished rather easily. So if we have Boehmite, we can see it very easily with infrared absorption. The problem is, if we go back to our original example, we don't see Boehmite absorption when the stone is filled with Boehmite needles. Find a mistake. You do see, however, the usual friends of infrared absorption of corundum, 3309, a signal for perhaps kaolinite. That means mineral from the surface. And other things like that, but you do not see, the point is you do not see the Boehmite inclusions, the Boehmite signal, sorry. Here is a spectacular view in crossed polarized light of a purple sapphire from Umba, and you can see very clearly the twinning lamellae. It's not in all stones you can do a good picture like that, and the other direction of twinning lamellae, and at these intersections, you can see the Boehmite needles here. Now, if you look at it in reflected light, where the Boehmite needle reach the surface, you can see actually square-like intersections, and essentially, as you can see on these enlarged or sort of less enlarged pictures, it looks like there's nothing there. It looks like we have a hole. Now, people have been thinking that this may not be Boehmite for a very long time, so I pulled out a good old book by Schmetzer, 1986, that was in German. So a few of you read it probably. And what's interesting in there is that he's questioning the fact that it is actually Boehmite needles. He put a question mark already in 1986. That was 30 years ago. So the question has been there for a long time. Are those Boehmite needles really Boehmite, or aren't they? It's not that you don't find Boehmite in Corundum, really. But most of the time, when you do see a Boehmite absorption in Corundum, you see this. You know, you have fissures which are filled with somewhat star-like crystal here. They don't give a star, Martin. But they look like stars a little bit. And you see that in those fissures that are surface-reaching. So you think they are like surface-related occurrence. So you do see Boehmite in sapphires from any locality, but not in the Boehmite needles. Now, when I got that specimen, I started thinking really strongly about, what is a Boehmite needle doing in a Ramora flux synthetic ruby? This specimen was given to me by Judith Othmer, who was growing the Ramora synthetic rubies. Some of you might remember. And so I grabbed it one day just because I thought there was a fun inclusion. It took like a number of years, I'll be discreet, to give it to a student to figure out what was in there. And the student came to me and said, well, it's strange, there's a Boehmite needle in synthetic ruby. I said, yeah, it is. So you can see these Boehmite needles, there are two of them here. And lo and behold, at the intersection of twin lamellae, rather. So that is a very unique specimen, I think. Here you have an enlargement of the situation, so you can perhaps better perceive the two twin lamellae and the needle in the middle of them. And when you take a scanning electron microscope and you look at this intersection with the surface, you find actually there's nothing to look at. There is a little square here. It's essentially hollow. Nothing in there. So we carried that on to a large number of samples. I won't tell you about all the samples, but just a couple. Different locality, different colors. Here's a Thai ruby, quite a series of, again, very visible Boehmite needles. And actually, when you look at their intersection with the surface, again, you find essentially squares, but they are hollow. Some of those are really, really small. Some of them were less than 1 micron. So it was a heck of a job to try to figure out where they were on the surface with the SEM, but we didn't manage that. This is a Tanzanian purple sapphire, another one, with some Boehmite needles in there. And here is one intersecting in the surface. And it has a little concomitant fracture here, which is a common feature, actually, associated with Boehmite needles. And if you look at that surface with the SEM, you see here the needle here and this little fracture. And this one was actually filled, and actually, by chemical analysis, we could see aluminum and oxygen. And oh, perhaps that is actually Boehmite. Actually, it's not. Has no contrast with the alumina. It's probably powdered alumina that got in there during the polishing process. So we tried hard to find Boehmite in Boehmite needle. We tried with infrared, of course, trying to focus the beam in the area richest in needles. And didn't see anything where we're expecting Boehmite. We saw the other things you normally see, but we didn't see any Boehmite in hundreds of stones that show very obvious Boehmite needles and should show Boehmite spectra if indeed there was Boehmite in the stone. So if they are not Boehmite, what are they? Well, we believe that they are what's called Roche channels. Roche channels are not familiar to gemologists. Myself, I discovered them a few years ago. And they were first discovered by Gustav Rose, a German mineralogist, in 1868, who discovered them in calcite, as a matter of fact. And as you know, calcite can have twinning lamellae as well. And he discovered that at the intersection of those twinning lamellae, he had hollow channels, hollow canale, as the title says. So this, because they are empty, they became known as Roche channels. They became named after the author of the article because there was nothing in there, so they call them Roche channels. So that became a well-known notion in metallurgy, for example, because you find them in certain varieties of metal, depending on their crystal structure. But that is not something that percolated all the way to gemology for the longest time. And on the occasion of a diploma on actually misgrowth diamonds, as an aside, there's some curious features in there that I first thought were just dissolved dislocation. Then my friend Jean-Claude Bouliard at the Sorbonne, who is kind of a man who has a great erudition in crystallographic matters, told me, no, these are Roche channels. I said, what the hell is that? So he explained to me what they were, and that ended up giving a small article about the presence of Roche channels being first described in diamond 2 years ago by my student at the time, Mary Shore. So this is what they look like with the SCM. You recognize that kind of crystallographic shape here. And this is basically a schematic on how it happens. You have the intersection of two twinning lamellae, and there at the intersection, you're not always, but you may have a hollow space. You're almost tempted to call that a negative crystal, but it's close to a negative crystal, but it's similar notion at least. So we find them in diamond. So they are described in calcite, they're found in metals, we find them in diamond. And then I wondered, well, we have been wondering about those Boehmite needles for a number of years now. Could they be Roche channels? And actually, what we think they are Roche channels. Why? They are hollow and empty. And that's what makes them extremely visible. Because if you think about it, there was Boehmite in there. Boehmite is about 165 refractive index. Corundum is about 175. That's 0.1 contrast in index of refraction. They wouldn't be that visible. They are extremely visible. But the fact that they're hollow matches that extremely well, because then you have a contrast between 1, roughly, the refractive index of air, with 175. That's 0.75 refractive index contrast. Then that perfectly explains why they are so visible even when they're tiny. They may be rarely filled with Boehmite. It might have been that on one deposit, they were actually all filled with Boehmite, and the name came from that. I haven't dug out into the history of that expression. But more often, you find some stuff also in these features, and it can be extremely varied in chemistry as in texture, and it's just stuff coming from the surface that happened to fall into that hole. And another indication that they are hollow is that when you titanium diffuse sapphires, for example, the titanium and therefore the color goes very fast through those features, which shouldn't be the case if they were full, and is the case because they are hollow. Now, how do they form? You have to have those twinning lamellae. These are generally the result of what is called deformation twinning. The mineral was squeezed. That created some kind of internal arrangement to rearrange and adapt for that deformation. That creates twinning, and we know that along twinning planes we tend to create vacancies, and deformation in general tends to create vacancies, confer brown diamond, for example. And these vacancies might migrate and create larger voids. And these would be the Roche channels. So I think we have a very good case in Corundum to say that what was called Boehmite needles is actually Roche channels. So even if we've thought for a couple years that they might be Roche channel, I'm getting now to the point where I'm actually stating they are Roche channel. And so we propose to just phase out the Boehmite needle expression, which is still fairly common actually in gemological articles, and get rid of that and replace it by Roche channels. It raises an almost philosophical question, because these are hollow. So how do you prove the nature of something that is hollow? There's nothing there to look at. When you have a mineral inclusion, you can identify the inclusion. When it's hollow, well, what do you do? Okay, so you have to go with whatever is available here, the morphology of these things, where they are very specific areas and all that. Thank you very much for your attention.
Good job.
You didn't expect any less, did you?
No, I didn't. Thank you, Emmanuel. Do we have any questions?
I was wondering, how did they come up with Boehmite in the first place versus some other?
Yeah, well, that's a question I've not really researched so far. I mean, I tried to dig out. When I realized he was in Schmetzer book, I said, oh, that's a pre-86, so it's going to take a long time, you know. You got to have an archival person go through the Corundum article. I mean, if any of you want to do that, and find out when it was first used. It's a huge amount of work, if you think about it, you know. Dig out the old gems, gemology, Journal of Gemology, all the German literature and all that, and see who first said it was Boehmite needle and where that corundum came from. I think it was probably in one locality when these things were filled with Boehmite, because that's a surface-related material. It's basically hydrous corundum, to make it simple. So it's very logical to find it associated with corundum, but most of those features are actually hollow, and that's why you see them so well.
Sir.
Yeah, Emmanuel, the mirrors that you showed you, especially the diamond, they form under high pressure. So how can you have empty space that has to be filled by something, fluid or something has to be in there?
That's a good question, but it's, again, if it was not innocent, if I said convert to brown diamond, you do find empty space in brown diamond, vacancy clusters, you know, and they were formed under high pressure. That was formed by plastic deformation as well. So we have another example in a totally different gem, which was under high pressure, where you do find actually not as large voids, but, well, actually in the case of that particular diamond, yeah, they were very large voids, but that's totally exceptional. And these are diamonds, you know, the mixed growth diamonds. So they are not exactly your run-of-the-mill diamond. They have the hydrogen rich and all that, so we don't know much about actually how they grew, as you well know, I think. Because hydrogen-rich diamond is, or cuboid growth sectors, it's just almost a different material from your normal octahedral diamond. So, you know, there are too many things that are unknown to really come to a coherent conclusion on that. You know, but it's true that it's funny to find empty spaces. That's why it took so long to recognize that, I think. That because people are not ready to admit that this was empty.
Anyone else? Yes, sir.
Brian.
Slightly less technical question. Could you please explain what is the DUG?
The what?
The DUG.
Well, this is not the subject here. He wants, he wants me to do advertisement for my gemology diploma in the University of Nantes. He was part of the first group to take it in English, so I do an advanced gemology diploma in Nantes. Here you have it, Brian. Yeah, he's the salesperson for the program, apparently. Yes?
I believe your first slide you said that the needles are one-dimensional.
Well, essentially one-dimensional. You know, I mean, this is something that's so small. With a normal binocular, they'll be one-dimensional in that sense that they have. It's very difficult to see how large they are, or measure is a better way of saying it, how large they are, because there are some are very, very small, less than a micron.
They seem to go down through different axes.
Yes, they do. They are almost 90 degrees to one another. What is it that you're not catching in?
One-dimensional.
Oh, well, it's just, yeah, compared to, you know, mineral inclusion we are more familiar with, which are larger, they have a thickness and all that. You know, that's why I was saying that, because sometimes they are so thin, you know, like a hair. You know, you can't really say how large they are. Yes?
How often do you confuse them with negative crystals?
Can you speak louder? Sorry.
How often do you confuse them with negative crystals?
Oh, okay, well, it's something that we looked at first. We saw, could it be negative crystals? I mean, if you look, you have to have some very large ones to be able to observe that conveniently with a binocular. So already you start with a non-typical, which is not a good way to start. You'd rather start with a standard. And there was one Tanzanian sapphire where they was absolutely huge, and you could actually see the negative faces and measure them. So with much serendipity, they were measured. And lo and behold, they matched the faces of the rhombohedron. So it's why I'm reluctant to say they are negative crystals, because I am not sure, you know, if you say a negative crystal, that relates to a growth phenomenon. This is a deformation phenomenon. So that might be to some degree misleading.
Okay, I'm afraid we're going to have to stop there.
I try to be short.
Nevertheless, we do. The next session starts. Yeah. Thank you, Emmanuel.